Okay, we're going to continue learning about how to sketch polar curves, and after a few examples we're going to try and understand how to work out the actual slope of a polar curve at a particular point in the classical dy dx, how far up and how far down by how far along. So last time we did this polar curve, and we sketched it and we found that it was something that looked like this. It actually went around 2 times, right? So here was 1 and here is 2. So we started here, of course, when theta equals 0. Okay, so second part of this question is rewrite this polar equation as a Cartesian equation. So we use the word Cartesian because the invention of, or the concept of identifying points in the plane with coordinates is from this French philosopher, mathematician called René Descartes, and so Cartesian is the reason, the reason we say Cartesian is because of Descartes. Okay, so this is our polar curve, and what do we have to play with? Well, we have our relations between polars and Cartesian equations, right? So what we know that x is equal to r cosine theta and y is equal to r sine theta. So we have this equation here, which involves r and theta, and we're going to somehow try and turn it into an equation just in terms of x and y. So if you look at this guy right here, the natural thing to do is to multiply by r, right? So if we multiply by r, so if r squared equals 2 r of theta cosine of theta, then we start to feel happier because this r cosine of theta, we can now think of this as just being x. R squared, well, r is just square root of x squared plus y squared. So this thing, when you write it in Cartesian equations, it's just going to be x squared plus y squared is equal to 2x, right? We can clean that up a little bit. Put the x on one side, right, just like that, and then this starts to look like what this looks like, which is a circle. So in order to get it in the form of a circle, we want to complete the square here. So that's the same as having x minus 1 squared. If we do this, then we're going to have a minus 2x, but also a 1, which is an extra term, so we're going to take it off. Subtract the 1. So this thing is the same as this thing because expanding this, x squared minus 2x plus 1, but then we get rid of the 1 with this minus 1 here. So we get the same thing as before, but now we see what we're doing. We have this x, so 1 squared is equal to 1, and sure enough, that's exactly the equation of a circle. That's the thing exactly distance 1 away from the point 0, 1. I mean, we have the picture right here. Or 1, 0, I should say. So this is 1, 0, and all the things exactly distance 1 away will be a circle around this point, and that's what we have. So our rewrite of this guy in Cartesian equations confirms the picture that we got when we tried to sketch this polar curve. Okay, so when you see this in general, you have some sort of polar equation. Try and do something so that you can turn it into things just involving x and y. And in all the examples you'll face, it shouldn't be too hard to do that. And in this case, just multiplying by r is the obvious thing because we want to get this r cosine theta form to replace this part by x. So that's how you do this kind of stuff. All right, let's do another example of sketching a polar curve. Okay. Change colors maybe. This is example 7. Sketch the curve Okay, so again, this is a new skill for probably most people. And at worst, you can just take a bunch of angles, put some kind of a table up like this, where you put the r of theta here. Actually, no, let's put the angle here. Yeah, theta on the other side. So the angle here, and we do r of theta here. And then we just put in very specific angles, whatever, pi over 6, and then whatever the r is, and so on, pi over 4, as we did before. And then you can just take your picture right here, and where you have the angle pi over 6, whatever r you find, just put a dot here. Well, this is pi over 6. And when you have pi over 4, whatever r you find, put a dot here, and you start to connect the dots also when angle 0. So you can do something like this, which is kind of the analog of when you were first learning about graphing functions. You would just take values on the x-axis, put in f of x, and just connect up the dots. But you don't want to do that very much, because it's a very slow and boring way to do it. And just as when you learned to do that for Cartesian equations, you fairly quickly found that your brain would just see the equation and be able to see what picture it would be forming. That's what's going to happen after you practice this for a little bit. In fact, it'll happen a lot faster than when you first learned it for Cartesian equations, because you've had many years of math since then, probably. So this is our guy, and this is my suggestion for this. Draw two pictures. Firstly, draw some kind of axis, and then draw the graph of the r of theta as theta varies over 0 to 2 pi. So what is this guy? Well, this guy is just sine. So first let's do sine. So what's sine going to do? It's going to go up. It's going to go down, and then it's going to go back here. So here we are, pi. This is pi over 2. This is 3 pi over 2. And this is 2 pi. And then we're just shifting it up by 1, right? So here's 1. So let's do this. If we shift, doesn't look too good. Shift everything up by 1, then we here. Around here we cross. Here we cross. Here we cross. So that's our guy. So this is r of theta right here. Okay. All right, so what is easier about this guy is that it's always going to remain positive, so we don't have to worry about reflecting through the origin as we did when r became negative in the last example we did. So let's just start and see what happens. So we start when the angle is 0 here, and then we are at 1, so we're here at 1. Should try and give yourself space to draw the thing. So here we are at 1. And as we range from 0 to pi over 2, we're going to go up to 2, right? We're going to go up to 2. So let's extend this picture a bit. This here is 2. And we are somewhat increasing smoothly. So as the angle goes from 0 to pi over 2, we continue to get something which is like bigger. So let's do this. Like 2 is a little bit too high. Maybe we should put 2 here. This is 2. Okay, so let's change color. So, okay, so what did we do? We did this part right here, which is this part of the graph. So let's put little circles around to indicate what we've done. So this is this part right here. And now we're going to do the part which is from pi over 2 to pi. So we're going down from 2 back to 1, right? This is pi over 2. I'm going to go to pi, and we are going to have that the radius is going to go from 2 down to 1 again, right? So this is, here is 1. And as we do this, I said 1 and I wrote 2. This is 1. As we do this, we're going to go down, 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 and we're going to end up here. Should be symmetrical, but not quite. Right, so actually a cool idea would be to change colors and put some dots here. So we are doing this part right now. Or we just did this part right here. So this is what we have right here. Right? And then on this part, what happens is we go from pi to 3 pi over 2, then the radius is going to go from 1 down to 0. So we're going to do this part right here. Okay, let's do this part right here. There we go. So radius goes from 1 down to 0. So it's going to, so here it's 1, and then as we keep turning and turning and turning, the radius gets smaller and smaller and smaller. So it has to sort of bend in like this. It's going to kind of look like this. All right. And let's take some colors. Here's our colors. So this is the little red dots I want to put, indicator going around. And then the final part is right here. Do I have another good color? Not really. Maybe green. This part right here, from 3 pi over 2 to 2 pi. So this part right here. And we're going from radius 0 up to radius 1. Radius 0, angle increases, goes up to radius 1, something like this. Okay, and that thing is a sketch of the polar curve. And as you can guess, this should have been symmetrical across the y-axis, and my picture doesn't reflect that, but this is the essence of it. Okay, and it's not, it's easier than the first example we did. It's certainly a lot faster than plotting in all these angles. So try and do this to yourself. Do the same stuff I'm doing. So each little part, try and give it a different color so you don't get lost as to which part you're doing. And you should find that this isn't incredibly hard for you after a little bit. All right, let's erase the board, do another example. This is example 8. Sketch the curve of theta is equal to cosine of 2 theta. Okay, this is going to be a bit more intricate. So as always, we're going to start by plotting the graph of the R and then following it around. So let's make this pi. This is 2 pi. This is pi over 2. This is 3 pi over 2. And this is pi over 4. This is 3 pi over 4. This is, I guess, 5 pi over 4. And this is 7 pi over 4. Okay, let's plot the graph of r of theta, which is 2 cosine theta underneath here. So what's going to happen? So we are starting here at 1, and to go from 0 to pi over 4, since we're multiplying the angle by 2, then we're actually going to go from 1 to 0 with cosine, right? So just, what is this doing? This is just multiplying theta by 2. So it's, as you range from 0 to as a range from 0 to pi, it's like inside cosine, it's like going from 0 to 2 pi. So whatever we see from 0 to 2 pi with cosine, we're going to see from 0 to pi with this particular guy, right? So we are going to go like this. Down. What a bad start. Down. And like this. And then like this. Here we are back at 1. Crossing 0 again. -1. Crossing 0. And then at 1. Okay, that is our guy. So this here is 1, and this is -1. Cool. All right, convince yourself that this is true before anything else, because this is important. And then I'm going to put our axes here. Let me do a different color, perhaps. And we're going to try and do this. All right, so same advice as before. So in each little stage, plot it individually. If possible, change colors. We don't have enough colors to really do this, but let's give it a go. So let's do the part which is from 0 to pi over 4. So let's put the angle of pi over 4. The angle of pi over 4 is like this, right? And then we're going to go from radius 1 down to radius 0. So if this here is... I'm trying to make this picture big because it gets complicated. If this here is 1, then as we do this thing, this part right here, the red part, as we do this part right here, we're going to go steadily from 1, where as the angle goes towards pi over 4, the radius is decreasing. So it goes from 1, and it's smaller and smaller radius, smaller and smaller and smaller and smaller and smaller and smaller, and then like this, and then like this, and then we're going to hit like this, right? This will be the first part. Even label it, so let's label this, say A. So this is A. Okay, let's do the next part. So now we're going to go from pi over 4 to 2 pi. So it's this part in blue. I hope these colors are visible to you guys. So pi over 4 to pi over 2. So here we have a problem because, well, not a problem, but here we have to pay a bit more attention because the radius is going to be negative now. And as I explained last time, I don't like to try and do two things at once. It's a recipe to make a mistake. So I'm going to first, instead of plotting R, I'm going to plot the absolute value of R. So I'm going to ignore the fact it's negative. I'm going to plot the absolute value of R, and then after I've done it, I'm going to reflect it through the origin to get actually the real thing we're looking for, which is R. So if I was just plotting the absolute value of R, so it would be the function which kind of does this, which goes up like this, then what would happen? Then as we go from pi over 4 to pi over 2, we go from 0 to 1, right? So let's plot this guy. So here is 1. Let's increase this a little bit. So here we are at 1. And what we'd be doing with the absolute value of R would be going something like this, right? It would be going like this, increasing, 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 increasing. This would be the absolute value of R of theta over this range. Strictly speaking, what I'm plotting is this, right? This would be this. You know? But we're not interested in that. We are actually interested in theta itself. So every time we have this guy, we're going to have a mirror image on the other side, right? So this guy corresponds to this. Well, let's do it slowly. This guy corresponds to this guy over here, this guy to this guy, this guy to this guy. We're reflecting across the origin throughout, this guy to this guy, this guy to this guy. So what we see is that the reflection of this shape across the origin gives us something like this. And my fear is that the blue is hard to see, so I'm going to sprinkle this with like dots of, not red, of green, say. So this guy is this guy. This is our actual guy, right? So that now that we've done this part, we don't need this anymore. Well, actually, let's just keep it. Let's just keep it. Why not? All right, so, and let's also label. So let's call this thing B. So we know that this guy here is B. That's the next thing we've done. All right, and let's do the next part. So from pi over 2 to 3 pi over 4. Again, we got a negative radius. No, which color? Let's say green. Okay, so we've got a negative radius, so it's going to go from -1 down to 0. So if we plot the positive radius first, again, I don't want to do two things at once, then as we go from pi over 2 to 3 pi over 4, then we're going to go from 1 down to 0 for the absolute value of r. So this thing here is the angle 3 pi over 4, right? And if we are plotting this guy, then we go from 1 down to 0. So it's going to look like this. Again, this is the absolute value of r, not the guy that we want. So let's do this guy right here. The picture gets crowded a little bit. All right, and now let's do the actual guy we want. So let's choose the color, the green color, right? So it's actual this thing that we want to plot. Right? And it's the mirror image of this guy. So this guy here, this is mirror image over here. This guy here has its mirror image over here. So I say mirror image, but I mean reflection through the origin. So it's not mirror in the sense of reflection through a plane, which is what you normally associate with mirror image. But as you do more maths, you'll find that there's more than one way to reflect. You can reflect through a line, and that gives you the kind of mirror image you might be more used to. You can also reflect through a point, and that is also a mirror image. And that's in some sense quite a natural one. So that's what I mean by mirror image. Okay, back to this task. So we are doing this guy, the mirror image through the origin. So as we go along here, a guy like here, this guy corresponds to this guy corresponds to this guy corresponds to this, and we've got something like this, right? The green is very visible. Let's label this thing C. So this is C right here. Cool. All right, so now we're kind of happy because we are now back in positive radii. Now I think we can get rid of this thing because we just needed it as a device to deal with the negative radii. We've done that for the time being, so let's just get rid of it. Okay, so we've done C. We are now going to do 3 pi over 4 to pi. Let's change colors. Let's go back to red. There isn't any choice. So we're going to do this thing. We're going to do this thing right here. Okay? We're going to do this thing right here. And it's positive radius, so we don't have to worry about reflecting through the origin. We can just plot it. So where are we? We are here. We are here with the angle, even though we just ended up here, we are here with the angle 3 pi over 4, and we're going to go to pi, right? So as we're at 3 pi over 4, the radius is 0, and as we go up to pi, the radius is 1. So over here is pi, so we are going to end up here, and we're going to do something like this. Yeah, that is this part, so maybe let's just put little crosses on here. Little crosses over here. And let's label it. So this is part D, and this is part D. Okay. Cool. And I hope, again, that's visible. All right, so now we're going to do pi to 5 pi over 4. Again, we are happy because it is positive radius, so it's this part here. So we don't have to worry about reflections with the origin. It's this part here. So we start off at angle 1, and we're going to go down to 0. So here we are. This is pi, and as we go to 5 pi over 4, this here is the angle 5 pi over 4. So we're going to do this thing. like this, right? And let's put some little circles around here, or squiggles at least, so that we identify a bit more which part we've just done, and we're going to give it a label. So we're on D, so this part must be E. E. And just because I'm fearful that you can't see that well, let me put these green dots here. Make it a bit clearer. All right, so we're here. Now we're doing 5 pi over 4 to 3 pi over 2. And now we've got, again, negative radii. So we're not going to do this in one stage. We're going to do 2 stages. We're going to go back to considering the absolute value of r first, right? So let's do that. So this is our part right here. And we're going to consider the absolute value of r. So this is the angle 5 pi over 4, and we're going to go from 5 pi over 4 to 3 pi over 2, right, which will be like this part here. But we're going to, first of all, consider the absolute value of r. Our picture's looking indeed crowded. So if we were just considering the absolute value of r, what would it look like? So this would be this guy right here. This would be the absolute value of r, right? So if we were just doing this angle from 5 pi over 4 down to 3 pi over down to 3 over 2 pi, then we'd have angle 0, and then it increases. In other words, we'll be just sketching over this curve that we already have, right? So I don't know if I want to write over this now because it's already got something there. So let me just do this. So this thing actually is also r of theta. I'm not going to put the other part of it. It should be okay. Maybe I will I just don't want to write nonsense. This is also this, over the range 5 pi over 4 to 3 pi over 2. So if you've never seen this stuff before, you will definitely need to watch this a number of times. This isn't that easy to begin with, but it will become easy if you do keep watching and keep trying this. Okay. So that guy is the absolute value, but we're not doing that. We're considering actually the real guy, which has got a negative value, so it's got the antipodal point. So antipodal means reflection through the origin. So this guy right here, with respect to the absolute value of r, gets reflected to this guy right here. This guy here gets reflected, this guy right here. This guy right here gets reflected to here. This guy gets reflected to here, and you can see what's happening. We're going around like this. So what we actually have, what color am I going to choose? Let me choose the green color. When we do this part right here, then we are actually doing this part right here. Like this. Okay. So this is F, and this is F right here. Okay. Cool. Now that we've done that, we don't need this thing anymore. Let's rub it off. Well, actually, it wouldn't have been bad to keep it. Too late. Okay, we're not done. So now we do from 3 pi over 2 to 7 pi over 4. Okay, again, we've got negative radii to worry about. Let's first think about the absolute value. The absolute value would be like this, right? So the absolute value would go from 1 down to 0. So where are we? So this is 3 pi over 4, right, over here, and down to 7 pi over 4, which is this angle right here. And if we just consider the absolute value, then it's exactly going over this part right here. So this thing is our absolute value, r of theta, comma theta, over that particular range, right? 3 pi over 2 to 7 pi over 4. Damn, closed interval, right? That guy is this guy. But, again, we are with negative radii, so if we choose red here, let's do red with some orange circle. So this is the part we're interested in, and it's the reflection of this guy on the other side. So this guy corresponds to this. Well, actually, sorry, let's start right here. We're starting here because we are starting at 3 pi over 2. So this guy corresponds to this guy corresponds to this guy corresponds to this guy corresponds to this, reflecting through the origin, this. So we're going to curve like this. What color have we chosen? We've chosen red with orange dots, so we're doing this. We're almost there. And then orange dots. And F, G. So this is part G. So this is G. Yeah, final bit. And now we're happy because we're back in positive radii again, right? So we can get, let's keep this and give an explanation of what it is. So this part is absolute value theta, as is this part right here. Cool. So this is our final part from 7 pi over 4 to 2 pi. We have positive radius. We start with radius 0 and go up to radius 1. So we ended up down here, and this is indeed the angle 7 pi over 4. So let's choose our color. Let's end with green. So this is the guy right here we're doing here. And when we are at angle 7 pi over 4, radius is 0, but then it increases, and it hits like this. FGH, so this is H right here. This is H. And that's it. Now we've done the whole part. Okay, so kind of a pretty shape we've got here from a very simple equation. And yeah, I hope you're not intimidated by this process. This is not in itself particularly difficult, right? So we just have to do it one stage at a time. We have to break it up into each of these little pieces, okay, where something happens. We go from 1 to 0, or 0 to 1, or 0 to -1, and draw each piece in turn, yeah? Just keep your head, draw each piece in turn. And when we have negative radii, my advice is that you learn to do this by first plotting positive radii and then reflecting through the origin. I've been doing this a while, and that's still how I do it. So maybe some of you can get beyond that and just do it in one stage. But if you're doing this for the first time, I would suggest you don't even try it. Do it this way. Plot the positive radii first and then reflect it through the origin to find out what the curve actually is. But most of all, don't be intimidated by this. If you've got this far, if you can sketch graphs from Cartesian coordinates, then you can also do this. It's just a different framework. Your mental muscle will develop to do this. This isn't an impossible task, and this is what you're here for. You're here to develop these new mental facilities, mental muscles to do this new kind of math. So do not give up on this. This is the final part, final important topic of the course. It definitely will be examined. So you need to maintain energy and learn this. Okay, let's do some other example if we can. Okay, sometimes we're going to have an equation, which isn't an equation for the radius, but an equation for the angle. So this is example, I don't know what example. Sketch the curve given by theta equals 1. Okay, so what is meant by this? Well, you're used to being asked things like sketch the curve of some equation like x squared plus y squared equals 1, which would just be a circle. Now we have an equation in r and theta, but it's just an equation in theta. That would be in the Cartesian equations, Cartesian coordinates equivalent to saying sketch the curve given by x equals 1, right? And x equals 1 is just all the x and y such that x equals 1 is just a vertical line going through x equals 1, right? This is a very similar kind of game. So, solution. So we've got to think about all polar coordinates are theta where theta equals 1. So if we do our little graph right here, then theta equals 1, well, what's that? I guess that's the angle like this. And since r can be anything, then that's going to include everything like this. Every positive number, so r comma 1 for any bigger than equal to 0. However, we also know that for negative r, this thing has a meaning. And for negative r, it is just the opposite side. It's the reflection across the other side. So since it doesn't specify anything for r, we have to assume it also means that r can be negative. So if r is negative, then it's going to be on this side as well. Right? So this is where r is less than equal to 0. Yeah? So actually this curve given by theta equals 1 is just this line here where the angle made with the line and the positive real numbers is 1, and it goes off like this and it goes down like this. Okay, cool. All right, let's erase the board. Okay, let's talk about symmetry. I think there's 2 m's in symmetry. Okay, if we have a polar equation that has some particular nice form, so if we have that r of theta equals r of minus theta, let's think about what that means. So if we have our coordinates like this, then if this thing is theta, then minus theta is right here, right? So if we plot r of theta being here, then they also have r of minus theta is here. So if we imagine what happens, what we have is that something which will be reflected across the x-axis, right? So if whatever we have, something like this, then it's going to be something like this. So symmetrical. Across x-axis. And if we have that r of theta equals r of theta plus pi, then what happens? Then, change colors. If we have something like this, if this is theta and this is r of theta, then r of theta plus pi is the opposite angle right here. Huh? So this is theta plus pi. And if r of theta plus pi has the same value of r of theta, then we're going to have a point like this on the other side. Right? So if we think about what that means, it means every point has a exact other point reflected through the origin, right? A so-called antipodal point, right? So that is symmetrical through the origin. So we did this r of theta equals cosine of 2 theta. That guy had that property, right? It was something like, it was like this shape, like a flower, like this. I'm not doing it the way we actually figured it out, but okay, very bad picture. But if this was the picture that which we came up with the last time, we see it has this property that every point has an antipodal point, right? Which has that kind of symmetry. It also has this property, which at every point has a point like this. Okay, so this is an example of a guy that has both those kinds of symmetry. So if you can observe that, then you save yourself, perhaps, or at least you can confirm that your picture is got properties that that it should have. I've not actually found these things to be useful or particularly useful when sketching curves themselves. So when you're sketching Cartesian functions, then if you know something symmetric, then it's very useful if it's symmetric across the y-axis, and you just plot everything for positive x, and then you know it's exactly the mirror image on the other side. These guys I don't find as useful because I have to go through the entire thing. So, but it is useful to check that you've got something correct. So we should definitely keep these things in mind. Okay, cool. Finally, let's talk about let's talk about slopes when we have a polar equation. So or I should have a polar curve. Okay, so let's draw a picture of a polar curve. Suppose you have a polar curve which is sort of, say, doing something like this. And suppose you want to figure out its slope at some particular angle. Suppose this is the angle we're interested in. This is angle theta. And we want to know the slope of this curve at theta, right? So this is our curve, r of theta. R of theta, theta. Okay, so just as when we discussed for parametric equations, this thing has no meaning in the standard way. There's no variable. This thing is not a function of x. We can't differentiate with respect to x. What this means is the slope in the sense of how far up or down we go compared to how far along. So we're going to have to work it out from this expression. We're going to have to get some expression for what this is in terms of stuff which we actually have, which is r and theta and its derivatives. And again, everything is just pictures, as I keep saying, as is the name of this actual channel. So let's work out the pictures to figure out what this can possibly be when we try and do this for a polar curve. So what can we do? So just look at the picture. So this is this thing. If we move forward a little bit, like to here, and suppose this thing corresponds to some little additional angle. So this is additional angle h. So this is like h as well. So then we are here. So this is the point. So I'm just going to write r of theta just to abbreviate this because I don't want to put too many. Okay, I've been consistent. Let me just keep being consistent. So, and this is the point, r of theta plus h, theta plus h. And what we're trying to figure out is the slope here, right? So if I drew the tangent line through this point, I'm trying to figure out the slope of this tangent line here. Yeah? So we're going to blow up the picture we see here. So imagine your magnifying glass is, magnifying microscope is taking this picture and blowing it up onto a much bigger scale like this. And I might run out of space. Okay, let's redraw the picture we have. It's something like this. Right? And this thing here is r of theta. Theta, this thing here is r of theta plus h. Theta plus h. And we're going to try and figure out the slope. So what could we possibly do for that? We just have to connect these guys and make a right angle triangle, huh? Made a right angle triangle like this. And then the slope is the limit as h goes to 0 of this divided by this. How far up we go divided by how far along. Yeah? So let's define this function x of theta to be r of theta cosine of theta. This thing gives us the x coordinate for every theta, right? Just by trig. And let's this thing be r of theta sine of theta. That's the y coordinate, right? So this distance right here is the jump in the x coordinate, right? So this distance right here, let me actually put the coordinate on the other side. So I have space to work. So arrow to coordinate over here. Let's do this as r of theta, theta. So then this distance right here is x of theta plus h minus x of theta. Yeah? And by exactly the same reasoning, this distance right here is y of theta plus h minus y of theta. Right? Because, again, look at this thing here. The x and y coordinates of any point are just given by this thing. So if we have a point given by some particular angle theta, its x coordinate is this, its y coordinate is here, just by trig, right? Just by trig. So the x coordinate right here is x of theta, and the y coordinate is this thing, y of theta. Okay, cool. Now, as we know, when we see an expression like this, we know that theta plus h minus y of theta, this is an awful lot like the derivative at h, and x of theta plus h minus x of theta is a lot like the derivatives times h. So I have pen death going on here. Let's change pens. Not much better. Okay. Stick to the same one. All right, so what is the ratio then? So the ratio, this dy by dx, I put in quotation marks because it isn't strictly dy by dx, is going to be just this thing divided by this thing. Okay, so I put, it's not quite equals because there's a slight error to do with the fact we're replacing this thing by its derivative times h, but the error is incredibly small compared to h. So as h goes to 0, the error goes away. This thing we can always do. This is completely mathematically correct and rigorous. Okay, so then we have just y prime of theta over x prime of theta. Yeah? Cool. And then we just have to figure out what these things are, which is easy because we have the expression over here, so we can differentiate them. So I'm fearful that I'm going to run out of space. So let me, okay, let me see if I can squeeze it in here. So x prime of theta, we have this, it's going to be r prime of theta cosine of theta plus or minus, I should say, minus sine of theta, right? That's this expression, and And where that sometimes down here you can't read it. So let's try. Let's hope this comes out. Okay, that's great. Let me just erase some of my diagram. And y prime of theta, just differentiating this thing, we're going to have r prime of theta sine theta plus r of theta cosine theta, right? Cool. So then we just have to put this into this expression. So this will just be r prime of theta sine theta plus r of theta cosine theta over that guy over there, r prime of theta cosine theta minus r of theta, r sine r of theta. I've dropped out this r of theta thing here. Sine of theta. Okay. And that thing is a completely explicit expression we can calculate, right? Because we're given the r of theta at some function, we can differentiate it. And then we just put in this thing for whatever the angle is, right? So we're going to give, if this angle was like pi over 6, we just put this in, and this would give us the slope, right? Cool. Now, the horribly nasty way to, well, I shouldn't say that so emphatically. The less good way to do this is that if you write this as dy by d theta over dx by d theta, then you can do this horrible thing of cancelling the d thetas and say, okay, well that looks like that, so that's the right expression. And indeed, that is how you might be tempted to remember it, and that might indeed be how it's taught to some people. But that's not the reason. The reason is the pictures, as always. Calculus is pictures, nothing to be believed, nothing to be memorized. It is just what your common sense and your ability to draw pictures, visualize this language, tells you. And I want you to not do this. I want you to draw these pictures, convince yourself that this is the meaningful expression for the slope, the half r up by half r down by half r along, which you can do. You can do that because it's just drawing this, blowing it up, taking a closer look. And once you've got this, then you know that this expression here and this expression here is well understood by these things, which we've done lots of times. And then that's it. Then you just put it in, the h's cancel, and you have your thing. Do this, convince yourself of this. Do not think of this as the reason or the important part. Just trust me on this. Okay, that's it for today.